post it out. All right, so here we're talking about robotic vision systems, okay? And vision systems basically have 5 major tasks. The first one is just part identification. So you have a camera connected to the robot, and you just are going to have parts coming down a conveyor or something, and the camera is just going to take a picture of it and just try to identify the type of part. The next one is kind of a little bit more advanced. Actually, the next 2 are pretty similar, or pretty much actually kind of tied together. The one is part location, and then the next is part orientation. Okay, so so a lot of times really it's really just the same thing. You're identifying where the part is and what the rotation is. And then there's the part inspection, where we're actually trying, using the camera, taking a picture of the part and looking at it and make sure that it meets given requirements within the image that we can see. And then the last one is range finding, just to identify where the part is. That's more for 3-dimensional cameras. So typically you need to have like 2 cameras, or at least a laser to complete the range finding. So let's just kind of go through each one of these here. So number 1, part identification. We want to just verify that the part is the correct part in there. Okay, we kind of talked a little bit on the things separately as part inspection, but we can, when we identify the part, we can also inspect it, at least certain aspects of it. Okay, and so with the vision system, you can compare an image of a part to the stored image located in the memory bank of the robot controller. Okay, so what we're doing is we're taking a picture. We're taking a picture of the part. We're storing that picture in the controller, and this is what we call teaching it. So we take a picture of the part, store it in the controller. And then as parts come down the line, we take a picture of each part coming down the line. And what we're doing is we're comparing it to that picture that we have stored. And if they match, then they match. If they don't match, then it's not that part. And so we didn't identify it. Okay, so if it doesn't match within a specific threshold, we don't find it. And so that's basically how these systems work. So they can't just like take a picture of a part and then try to identify it. All right, so the first thing you had to do for this to work is you had to take the picture of a known good part and store that in the controller. Okay. All right, so and you can actually take maybe several pictures and compare it and do several different comparisons and things. One of the things we can tell is the size, another is the shape, and also missing features. Okay, all right, so depending on your version of robot that you're running, some of the older robots, Fanuc actually referred to this as error proofing. Okay, so on like the R30IA robot controllers, when you would like go in to do the setup, it would like be saying, oh, well, this is error proofing. But on other robots, like the newer version of the robots, they actually call it vision inspection. Okay, so they use the term inspection on the newer robots, but the older robots, they use this term of error proofing. So just, pretty guaranteed there's a test question in there along the ways. All right, so here is a couple of pictures of a part. And when you first look at the part, they're very, very similar. All right, but what we see, of course, here is in the middle part here it is we have the part on the left, which is the one stored in memory. All right, and when you look at the overall shape and design and everything of the part, they're identical. The only difference is the center has a circle in the image stored in memory, but the image stored over here, or the image that we took as the part's coming down the line and we took apart, now all of a sudden we've got a square hole instead of a round hole in there. Okay, and so the question is this part different? Okay, so let me just you know, put that out there for you guys. Questions. How many of you think that this is the same part, and how many of you think it's a different part? Seems like maybe yeah, it's kind of a trick question. Okay, it's different in the center. Okay, however, when we teach the part, what we're really teaching is the edges. Okay, and so what we do is we get to decide, does this matter? Is it a round hole or a square hole, or can we ignore that center? All right, so when you teach the part, you teach it edges, anything that it can see. So you see, like here, there's some dark, and you can kind of see some shapes in here. But from this angle, straight above the part here, we really can't see these parts at all. They're just dark. All right. So, but what we can see is we can see the outside edge very, very well. And we can see the holes very well. Okay. So, you know, definitely just looking at them, yes, they're different. Okay. I agree. However, I could, if I wanted to, I could teach the robot. There's a feature they call a mask. Okay. And what I could do is I could draw a mask. Usually it's actually red. Let me flip it to red here. Because on the it's usually actually it's red. It's sort of like this red mask, but it's transparent when you're teaching it. And this is when you're actually teaching the part. So if you're actually teaching the part, what happens is, you know, you take the picture, and this is the picture you get. And then you throw this mask over it. And if I put this mask over the center hole, and in the stored image, and I mask the hole, then what I'm saying is all I care about is the outer shape. Okay, because I can't, like I say, I can't really tell about these dark areas here. Really hard to tell those. So what I'm looking for is the edges, and I have a later slide that really demonstrates that. But the outer shape of this is identical. And so if I mask the center here, if I throw this mask on the center, then these two parts now become identical to the robot, because what it's doing, because I've masked out that center part, which is obviously different, I'm saying ignore it. I don't care. As long as the outside edges and the things that are not masked are viewable, it's okay. The part is what I'm looking for. Okay. So when we teach the part, we get to tell it what is important to us and what's not. So if we think that the center hole is important, we remove the mask, or we don't put it on to begin with. And now we say that, yes, that center hole is very important, and therefore these two are absolutely different parts. All right, so the next two parts, as I said, are the same sort of thing. So part 2 here is talking about the part location. Okay, and so what we're doing is we've got the part, and it's coming down the conveyor, but it may not always be in the exact same spot all the time. And so what we're doing then is going to look at that, and it may be in a different part, in a different place. Okay, so it's the exact same part, but it's in a different place. And so what we have to do is, first thing we do is we got to teach it what the part looks like, just like we did for the inspection. So that part doesn't change. But now what we're going to do is we're going to tell it, we got to tell it where it's at. And so to do that, we actually have to create a frame. And I think I spoke a little bit about frames in the class earlier on, but we have to set up a frame and say this is where it's at. And just in general, this, and so basically what we would do is we would teach it the origin. So let me just kind of show you the a grid here. So this is a grid, and what we do is we set this underneath the camera, and then we take a picture of it. And so in this grid, then we're teaching it where the origin is at. So we're saying, okay, this is the origin, and this is the X direction, and this is the Y direction. Okay, and we get to choose this. You know, I could come along and rotate this grid or whatever if I wanted to. You know, so it doesn't matter what direction the grid is on here. Let's see, position and size. All right, so, you know, so I could come in here and rotate the grid if I wanted to or something. So I get to choose what direction X and Y is, okay? But once I do that, I set the grid, like, you know, I put that grid under the camera and I teach it, you know, well, this is my origin here, and this is the X direction, and this is the Y direction, or, you know, whatever directions I decide those are. And then I set the part down. And ideally, what I would do, let me grab a part here. Oh, that's all one big piece. Okay. So what I like to do is I like to take this part and set it down right at the origin. Okay. So right there in, or the center of the grid. Okay, so I like to make the center of the grid my origin now. This is like the default. This is just a grid here from Edmund Optics. Okay, so the grids vary a little bit depending on the manufacturer of the vision system, but I like to set my origin to be right here in the center. Okay, and then what I do is I take, let me shrink this down just a little bit, okay? But so I take this part, and I guess since I can't really see that anyhow, we'll call this the origin. So I teach, when I teach the part, I teach it wherever my origin is. So I mean, if we go with this origin that they're marking here, this is my origin. So I set this, you know, this is where my part is at. Okay, and when I teach the part, I teach this is the part and it's at the origin. Okay, and so now this is where the part's at. Now I teach my robot, I'm going to come over and pick this part up and put it where, you know, where it needs to go or whatever. And so it knows to come over here to this origin position and pick this part up. Okay, and so now as the parts come down the conveyor, the part might be over here, or it might be over here. And so the X and the Y position of that part are different. But since I've taught the grid, the camera, I taught the frame, and it knows where the origin is. It knows where the part should have been, which was over here. But when it takes the picture, it basically counts how many dots over in the X direction and how many dots down in the Y direction, and therefore it can figure out where this part is at. It knows the X and it knows the Y. Okay, so it can then take the picture and see the part's not at the origin, the part's over in the X and over in the Y, and then it can go and grab that part. All right, now a couple of things about this grid here. You know, what you, like I say, you basically, you take this grid, you stick it under the camera, and you calibrate the camera to the grid. Okay, and you got to make sure that, you know, once you calibrate it, that camera doesn't move. All right, so if it gets bumped around, you know, or it's loose because the machine's vibrating or something, and it jiggles around or something, then your X and Y's are going to be off because your camera has moved slightly. All right. However, once you calibrate the camera, it knows where that part is at. So even if the part is like way up here somewhere, okay, or way down here, even though it's not on the grid, it can, as long as the camera can see it, okay, just like you guys can see it. So like right now, if I take this and I kind of shove it off to the side, you guys can barely see it, right? It's just right over here on the side. You can't see it. So if the camera can't see it, it can't find it, right? That should be obvious. But as long as it can see it, okay, and or at least see enough of it to identify it, then it can come and find it. It knows, even though the grid doesn't go all the way over here to where this part is at, okay, the robot understands that, you know, that direction, that X direction is still going, that Y direction is still going. So if it can see the part, it doesn't matter whether the part is actually in the grid. Okay, the grid is just a reference point to line the camera up so that the robot knows what direction is X, where's the origin, what direction is Y, and then it can do the rest. You know, but it knows, as long as the robot, like I say, can see it, it can find it. Okay. The other aspect of this is actually the, you know, the next bullet point is the rotation. So I can take this now, and, you know, if this thing's rotated, you know, so here it is, it's rotated. All right, so remember we originally taught it as being over here at the origin with no rotation. But now it's rotated. So here this is rotated and shifted. But it's no big deal. It doesn't matter, because just as doing the X and the Y, you can also tell, okay, well, it's been rotated so many degrees. And so it'll understand that and be able to make the adjustments. So when it goes over and picks it up, it not only figures the X and the Y out, it figures out the rotation also. All right, so that's, well, they actually, I guess they're using the term here in the slides, orientation. So the orientation or rotation of the part, okay? So we can detect that also. So I pretty much covered all those slides just on that one, okay? All right, so couple of things about the grid here. The grid, you see the spacing of the dots, that spacing is very important, because, you know, it tells you how many millimeters apart it is, because, you know, you know that the further something is away, the smaller it looks. So even though it's the exact same size, if it's just a couple of feet away, it looks fairly large. If it's, you know, 30 feet away, it looks smaller. If it's 100 feet away, it looks much smaller. And so what we have to do as part of the calibration is we have to teach it these dots. And we have to tell it how far away those dots are. And actually, when you get a grid, like Fanuc robots, for instance, when you buy the IR Vision for a Fanuc robot, they give you several different grids. They give you a big one that's got big dots on it that are 30 millimeters apart. And then they give you one that's got a 20 millimeter, the dots are 20 millimeters apart. and then they have a 15 millimeter, and then they have a 10 millimeter one. They may even have smaller than that, but I know they have those sizes. And so when you calibrate that camera, right, part of the calibration process is telling it how far apart those dots are. Okay, and so that's that's kind of one key factor of the system there. And so when you do that, then you can also use that for part inspection. Okay, and so the part inspection piece here is using the same calibration. As long as the camera hasn't moved, it doesn't matter whether you're looking to pick it up and where it's at, or you're just trying to measure sizes and things like that. Either way, you need that calibration. Okay, and so what you can do then is you have your part here, and this part has different sizes, different parts. We have like the hole in the center should be 30 millimeters apart. The width of the entire object in this example is 180 millimeters apart. And so we can once we've calibrated it, we can then take the picture and make sure that it meets all the dimensions that we want to test, or that to verify that the part was made correctly. Okay, and so again, this is part of the teaching process. We have to take the picture, and then as part of that teaching process, we tell it, okay, look here between these 2 points and look at this and see what is the distance between those two edges, or those two identifiable parts within the whole part, and make sure that if it's supposed to be 30 millimeters, it's 30 millimeters, and if it's not, then we say this part's bad, or we send it back and get it reworked, or throw it in the scrap pile to be remelted down, or whatever, depending on what the options are. But this is the part inspection. So again, it can use the same calibration that the orientation and position things use, and so you can really kind of do all of those, right? With the exact same camera, we can do all of these that we've discussed so far with that one camera sitting in that one spot and just taking that picture. Okay. Now, one thing I forgot to mention about this grid, I want to make sure I do mention, is that once you've calibrated the camera, the grid is no longer needed. Okay, it doesn't need to look at those dots every single time. And as a matter of fact, a lot of times looking at those dots will mess up the identification of the part, because you see the black dots now in the image that they stuck in here. You kind of have a little bit of a band all the way around it, so it's covering it up. But that's just because it was kind of a screenshot covering that up. But if the real part, these black dots here would be blending in to the grid, and the shape wouldn't look quite right. All right, and it'd actually be hard for it to identify. So once you calibrate that camera, you take that grid and remove it. The other thing is, these grids are either kind of maybe a thick paper or a thin piece of plastic or something. But if you got heavy parts moving down the line coming across this, they're going to scratch it and tear it all up anyhow. So once the camera is calibrated, that grid can be removed. As long as the camera does not move, it knows the calibration, it knows its XY, it knows the distances, and so the grid is no longer needed. The grid is just a teaching tool or calibration tool. All right, so the next thing is range finding. Okay, and range finding is now to try to identify how far away the part is. Okay, so when we're doing all these other things here where we're trying to find the position or the rotation of the part and the position in XY and the rotation, one camera is enough for that. Okay, and we're good. But now with range finding, what we need to do is we need to find out how far away the object is from the camera. All right, and so to do this, you need either 2 or 3 or more cameras, but you need a minimum of 2 cameras, or you have to have a laser. You can do it with just one laser. All right, but you need to be able to take, if you just have a regular camera, you need to be able to take at least 2 pictures now. And so the idea is that, as I said earlier, right, the further away apart is, the smaller it gets. And so the idea is that if you only have one camera and it's fixed, it can't move, then you only have one distance. However, you can do it with a single camera if you mount the camera onto the robot. So now if the camera is on the robot, you can move the robot arm up and down, and it'll know, how many millimeters you moved it up or down, and then it can do the math and calculate. So when you take a picture of the object, you can take the picture here, and you can take the picture there, and then you can calculate, well, how far away is it based on the size? And so then you can determine that, hey, the part's down low or up high, and so you can tell distance with one camera if it's mounted to the robot, but you still have to take 2 pictures. Okay, and that's why they say here 2 or more camera views. So that camera views could be done by one camera, but just having it mounted on the robot and having the robot lifted up and down to take those pictures. Okay, or like I say, with a laser. Now, one of the things that Fanuc Robot, I know, and I'm sure the other manufacturers have something similar to it also, they have what they call a bin picking camera. And it's actually one camera with 2 lasers kind of pointing down at angles like this. So there's one camera pointing down, and then these 2 lasers, and it sits over like a bin. So if you just had this bin full of stuff, and the idea is that with 2 lasers and that camera, you can actually identify the part, and you can see it in 3 dimensions. And so you can go in there and you can pick those parts out of there, even though they're just tossed in the bin in any way, shape, or form. And I'm told they work very well. I haven't actually seen one of them work, but they look and sound pretty cool. And but they're kind of expensive. I think they're like $30,000 or $40,000 just for the camera. Okay, and the software, of course, that goes with that to work it. But but yeah, so with the range finding now, we can find parts in 3 dimensions, X, Y, and Z. They could just be rotated and flipped, and we can see them see 3 dimensions now. So everything before this we could do with a single camera, but here we need at minimum 2 camera views, okay, or a laser thrown in. All right, so when we look at the cameras, it's kind of small up here. Let me blow this font up a little bit. I don't know why it's not really increasing, but we got 5 major components. Okay, so the first part is the camera, of course. Okay, and then the camera controller. Okay, which is like, really, it's the robot. The robot controller itself has the the software and stuff to take the picture. Or a lot of times, a lot of companies actually use a PLC that's taking the picture and then sending the relevant information over to the robot. Okay, so so sometimes the camera is hooked up to a separate system and then just communicating usually across some sort of network protocol over to the robot. Okay, and then of course we have the interface equipment like the cables, those sorts of things, and then we have a monitor. Now the monitor, like if you look over here, we've got a computer with a keyboard and a monitor over here. That's really just for teaching the part. Okay, so the once the part is taught, then the controller, whether it's a PLC controller or the controller of the robot itself, is actually going to take the picture, do the comparisons, do the math to figure out the X, Y, yaw, pitch, and roll, and all those different things, and that. So, the monitor here, where it says monitor, that's just basically to kind of see the part when you're teaching it. And they do have like a vision runtime feature that you can run, so you can say, you can watch as it sees the part, and you can say, oh, I didn't like that part, but you can kind of be watching it and see what it saw and maybe determine why. So just to kind of watch it as it goes. Another thing I'd like to say here, as far as the monitor and the computer to teach it and that kind of stuff, some of the newer robots, you can actually just do it all from the teach pendant. Okay, so the Fanuc R30IB controllers, they actually, you can teach the parts and view the runtime and everything right from the teach pendant. So you don't need to have a separate computer and monitor set up to do the teaching and just verifying the runtime. All right. So so that's kind of nice if need be. However, even on the R30IB with that on the teach pendant, I prefer having a large monitor instead of trying to look on that small teach pendant screen. Okay, because you can just see more, and it's just a little bit easier to work with. But you can do it if you need to, all on the teach pendant. And then of course the last thing is the light source. And when I say last, it's last but not least. Okay, lighting is critical to vision systems. All right, and so I don't, if you guys kind of see my my camera, I do have the camera turned on here today, but you can see the sunshine is coming in, and my blinds broke on my window, so I can't put that down. So it's just, I'm just being just very, very bright there, and so that's like an excellent illustration here about lighting. So when I was going through my certification training for the vision systems, we had these robots, and there was a group of two. Each group of two got assigned to these robots to go do the exercises. And I felt really bad for this one guy because he got stuck with this robot that had a skylight right above the robot. And it was a day that it was kind of a cloudy day, kind of a windy, cloudy day. Not real cloudy, but just like partially cloudy. And so he's like trying to teach this robot to see these things. And what happened, a cloud would come by, and it'd get really, really dark over that window. And so therefore the robot, the part he was looking at, was really, really dark. And then, so he'd teach the part, and then about the time that he's ready to go and see if it's going to work and go pick up the part where it's at and all that kind of stuff, the cloud would move on by, and then the bright light from the sunshine was coming down through there, and he was just having a terrible time. The rest of us, we were further away from that skylight, and we weren't having any problems. But he was having serious problems there because lighting is critical to seeing the part and being able to identify it. So all right, so anyhow, we'll look at lighting here. Okay. I'll come back and talk about these parts here, but I wanted, since I was spent so much time on lighting, okay, I want to I'm going to start with lighting, and I'll come back and look at the other parts here. So, the purpose of the lighting system is to illuminate the object to see those key aspects that you're looking for. Okay, so as I said before, when you're teaching the part, you're teaching it, this is what we're looking for, and you can tell it using that mask or whatever. I don't even care about the hole in the center. Or something like that. But you need to make sure that the robot can see those aspects of the part that you want it to see. Okay, we can also mess around with the lighting to suppress those parts that we don't want it to see. Okay, and then we can create contrast. Contrast is really very important for these vision systems. Okay, and so there's basically a few different things we can do here. One of them, we can do something called front lighting. All right, so we have the light in the front. We can do backlighting. Backlighting is really good for the inspection because it gives a nice, bright, crisp edge, so we can't really see the part well. It's kind of like that part that we had up above there with the hole or the square. We can't really tell a lot of the shape and stuff on it, but we can tell the edges very nicely. Okay, or then we can maybe use some angled lighting to see structure a little bit. So let's take a look here. So this is some front lighting. When you do front lighting, you get this nice bright field coming straight down on the part. And then that light, as that light comes down, it's going to be reflected. Okay, so it's the most common. I think part of the reason it's the most common, it's really the easiest to set up. You just put a light up here above the camera somewhere, and you can get it. It's good for a part that's not moving or a part that's moving kind of slow. Okay. All right, so the next is backlighting. That's where we put the light behind the we put the part between the camera and the light source, and so then the camera can't really see the surface of the part very well, and we're really just looking at any edges. Okay, and it's really good to see missing parts, or like, you can, back to that example we had earlier with the square or round hole. Since that's a hole, that light source is going to come right up through that hole, and it'll be very easy to see. From 330. It will be easy to see whether it is a round hole or a square hole. All right, so with structured lighting here, what we can do is we can actually, if we put the light at an angle, so notice here the camera is still looking straight down, but in this case they're using a laser, and with the laser, since a laser, you're just going to get a very thin line there. And so using that, this is the resulting image that we get there, and that we can tell this, that there's this rectangular piece coming on top of the block here. So we have kind of this block, and then we have this other rectangular piece on the other. And with this angled lighting now, we can tell the height difference there. All right, and not only can we tell that there is a height difference, but we would actually be able to know how high that is. So it, you know, we may have a couple different parts, one with a really high structure there and the other maybe not so high, and we'd actually be able to tell that based on this resultant image. Okay, so we can look and we can see the various structure or the shape of the object with structured lighting. All right, so some different types of light sources we can use. Of course, you know, if you can find them nowadays, it's kind of actually hard to find incandescent bulbs, but you know, just incandescent lighting, fluorescent lighting, just LED, ordinary LED lighting can be useful. You know, just something so that you get enough light to see the part. All right, but then we have two specialty types here, which are the strobe and the laser. Okay. All right, so, and of course, incandescent doesn't include the halogen lamps and stuff, and those are still available. All right, but the okay, so when remember, like we kind of talked a couple of slides ago about, you know, the just front lighting is good for slow moving parts or parts that aren't moving at all. However, if you have parts moving really, really fast, you know, if you just take an ordinary picture, it's going to look really blurry like this. Okay, so by using a strobe light, what you do is by taking a strobe light, you can, since you can only see that just that light for just a blink, it actually makes these fast moving parts look stationary. And so using a strobe light, you can sort of freeze the picture, the image within the picture, and not get that blur going. And that'll help give you a good picture even though the part is moving very, very fast. Okay. All right, and then of course lasers can be used to show that structure. Okay. All right, so here's an example of backlighting. Okay, and so you see here, looking down at this part, we cannot see this part very well from looking straight down on it. However, this red area down here is actually the backlight, and then once you turn that backlight on, it's going to light the edges. So we can't see the surface of the part at all, but we can see the edge, and we can see over here that this part is got this chunk missing out of it over here on the right hand side. And so the backlighting is very, very good for that. Okay. Another thing to be considering is the surface of the part you're taking a picture of. Okay, so if you have a light source and your part is really, really smooth, what will happen is, you know, it's like a mirror, and that light source comes and it hits the part and it bounces away, and this angle of reflection is the same angle, you know, effectively the same angle that the incident light is coming and hitting it here. However, if the part is rough, what will happen is some of that light, when it hits some of the higher edges of that part, they'll get deflected in a different way. And so by angling the lighting, we can see the texture of a surface. Okay, so by changing that angle, so instead of coming perfectly straight down, maybe we want to be at, you know, kind of that structured lighting, even with an ordinary light instead of a laser. But if we're shooting it at an angle, then we can, you know, if it's got a rough surface, we'll be able to detect that because the light's going to be bouncing in all kinds of different directions, and we'll be able to see that. or if it has a smooth surface, or maybe we're simply trying to tell, is this one smooth or rough, and that would be sufficient. Okay. Another aspect to consider is the color. Okay, colors make a huge deal, and so there's various different colors are kind of like like the opposites of each other, and for one of those it's green and red, and those are usually the most common. People who have issues seeing colors, they usually have the biggest issues with red and green together. And so this slide illustrates here what green lighting or red lighting will do. All right, so if you remember from the robots in class, right, Fanuc robots are yellow with red lettering. So the word Fanuc always shows up in red, and on the robots, and a lot of times on the packaging and stuff of those. And so here's an example. If I'm using a red light, I cannot even see the word Fanuc, even though it's there. Now, if you look really closely, right here, I don't know how well you guys can see that, through this projection here, but right along here, you can see just this C. This is the C from Fanuc, and you can just barely see it right there. All right, but if we use green lighting, we can read this entire word. So this is the same camera taking the same picture of this box, but we're using both red lighting and green lighting, and you can see the difference. With the red lighting, it's virtually invisible, and with the green lighting, it's very easy to read the word Fanuc. Okay. So colors, not only is the brightness of the lighting very important, but the color of the lighting can be used to see something that with a different color you can't see it at all. But if so if you're having trouble seeing something on a part, and especially if that part that piece within the part that you're trying to identify is a different color, you may want to look and see, hey, if I apply some different lighting, some different colors or light, put a filter over the light and to change the color, maybe I'll be able to see it better. Okay. So as I said, this lighting is very, very critical to your robotic vision system. Okay. All right, so given that, let's come on back and we'll talk about the rest of the components of the camera in a little bit more detail. So the first part is the camera, and of course the camera lens. All right, so the camera gives us the camera tied in with the camera lens gives us what we call the field of view. Okay, so the field of view here you have the camera, and then attached to the camera is a lens. Now you can put on a different lens, and that'll give you a different field of view. The field of view is the area that you can see. So like just right here on the slides that we have, right? If this part, if I slide this way over here, you guys can't see it because it's not in your field of view. So, but if I move it over here, then we can see it sitting in there. So the camera defines how much of an area you can actually see. Okay. And the way that works is it's based on these four parameters. You have something called the focal length. Okay. And the focal length is the distance from the center of the lens to the image area of the camera. Okay. Called this, usually referred to as the CCD. We'll look at that in a couple slides here. All right. So from the focal point of the lens, the center point of the lens, to where the image is actually going to be captured on here, okay, is the focal length. Then we have the width, okay, or the size. It's really kind of the width in both directions, so the width and the height of that image plate where the picture is being focused on from the lens. All right, so how big of a capture point do you have within that camera? How big is your CCD array? Okay, those two factors, and then how far away is your object that you're looking at? Okay, that's the standoff distance, how far away it is from the lens. Okay, and then, you know, and that gives us how big your field of view is. Okay, so these four values determine, you know, kind of determine your overall settings for your camera. So if you want a bigger field of view, okay, then you can either change your lens, or, you know, obviously get a CCD, change your CCD width. Now, you can't just change the CCD width of your camera. You would have to buy a different camera with a different width, okay? Because buying the camera basically says this is the width of your CCD, all right? You know, but these aspects here give you this ratio. So if you want a bigger field of view, you know, you can increase your focal length, okay, or change your camera, get a different width, or change that standoff distance. Okay, so by modifying these, you can change that field of view. All right, so now the key point of the camera, though, is that CCD. Okay, and so what we're going to do is we're going to take that picture, and what we're really doing is looking for either light or not light. And so that camera has an array on it. Let me jump ahead. I guess to this one. So CCD, I've been using this term CCD. CCD stands for Charged Coupled Device. And actually, we sort of talked about these back last week in the analog sensor. We talked about that photoresistive sensor, that analog sensor that is a kind of like a resistor where the resistance increases or decreases as the light intensity changes. Well, you take a whole bunch of those and put them in an array, and that gives you a camera, okay? And so what happens here, it's called charged coupled device. So what happens is the light hits these, as the light intensity hits these little resistive sort of things on here, and actually in reality for cameras, they're either light sensitive diodes or light sensitive transistors. And so what happens is you get a bright light on them, they basically allow a lot of current to flow. But if you have darkness, then you don't have a lot of current flowing. And so it could either be a diode or a transistor, but it's basically a solid state device that you have, you know, really hundreds and hundreds or even thousands of these real small transistors right beside each other in this big array. All right, so they're, you know, this is the array here, and let me zoom this up for a bit here. Right, so you see it, you know, it looks almost like a screen, but every one of these little dots is one of those transistors. All right, so there's, you know, literally thousands of these on a lot of these newer things. So this one here is actually for the Sony XC56, which is an industrial class camera, and it's got 659 of those transistors in one row, and there's 494 rows, and if you multiply that, there's 3,000 or excuse me, 325,546 transistors in this, and this is your CCD, okay? All right, and each one of those transistors is referred to as a pixel. All right, now these cameras and everything we've been talking about, even the colored stuff, you know, the coloring here, when we're talking about seeing this or not, notice everything here is black and white, because the camera, even though I'm using red light or green light, the camera is black and white, okay? So a lot of these industrial cameras are actually just black and white. So this camera here that you're talking about, which is the camera we have on the robots in the classroom, these are XC56 Sony cameras, and they're just a black and white camera. Okay. Doesn't mean we can't see colors, but we're seeing them as a shade of gray. So what happens is that light falls on them, we get an intensity. And actually, most of these are basically being fed into an analog to digital converter, which is only an 8-bit converter, which means that you can only see an intensity range between 0 to 255. So 255, it's as bright as you can detect. And 0 is black, no light. Which doesn't necessarily mean that there's no light at all. With the human eye, we might be able to see it and distinguish, but the camera can't see anything. You know, once you hit 0, you can't get any darker to the camera than 0. All right, and so so it ranges from 0 up to 255. And any various different shades of gray, 1 through 254, is somewhere in between there, right? So this is like bright white, as bright as you can get, and then 0 is as dark as you can get, but you can have any value between there. Okay. All right, so I already talked about the array piece. Okay. All right, now you know, some cameras, some newer cameras and stuff do have they do have color vision. All right, and so those actually, instead of having just one transistor, they're going to have 3 transistors. We're going to have one that basically has a blue lens, a green lens, and a red lens. So 1 pixel then becomes 1 pixel is actually made up of 3 transistors instead of a single transistor. Okay, and one of the kind of the qualities of the camera that they talk about is the dot pitch, and the dot pitch is the distance between the dots. Okay, and then they talk about the resolution, which is the how many dots you have. Okay, so a smaller dot pitch would indicate that the transistors are closer together, and that would be a much higher quality camera than one with a larger dot pitch. All right, so here is an example, and we're back talking to the black and white. Of course, the dot pitch and resolution apply whether it's a color camera or a black and white camera. Okay, but here's an example, and in this case, basically every one of these squares is showing a is a transistor, right? One of those light sensitive transistors or diodes inside the CCD. So this one here is just an 8x8, just a simple example piece here. But what happens then is if we have like the letter H sitting in the field of view of the camera, right? And so in this case, they're perfectly lined up. So the H, you can see it's making these squares dark. So these squares where the H is at aren't getting as much light as the other squares, and so we can see the shape of the H. Okay. All right, so when we add more and more pixels, we can get a better resolution. And so what this slide is actually trying to show us here is a line here. Let me just kind of grab a separate line. Okay, so let me pop this back out here. Okay, so my line width, my line color, just give it a bright color so we can kind of see it. All right, so when we have this line here, okay, the idea is that if we have a really low resolution, then we can't really tell the angle very well. So if it was just a 4 square, if you see these outer 4 squares here, this line could kind of rotate between here all along here, and it's barely hitting the white squares. You see, like right down in here, it's barely hitting the white square, even though I'm kind of switching it back and forth. It's just barely touching into the white right there. All right, and so with just 4 squares, it's kind of hard to tell the exact angle of this line. However, as we go to 8 squares or 12 squares or 16 squares or 64 or 256, as we add more and more squares, then it gives us a much better line of seeing, you know, exactly what is the slope of this line. Okay, and so, you know, the resolution is just going to show us a lot more information. Okay, so as we have a higher resolution, we have a lot more, we can see just so much more and tell so much more about the part, you know, which is true for any camera in any application. So actually that XC56 camera that we had on the slide a little bit before, you know, it was only a 65 or 659 by whatever, I forget the other height, but you know, it's very low resolution. It's less than a megabyte, right? It was like 350,000 pixels or something. So that isn't even a 1 meg camera. Okay, so if you think about your cell phones now, they have like 9 megapixel cameras or 12 megapixel cameras. You know, the resolution of that compared to 359,000 pixels, you know, it's just tremendously different. Okay. All right, so you know, so your resolution is important, but also how far away you are affects that, right? So you see here, it's like if I'm zoomed in on this, I can see this part, and you know, you see all the little squares are representing those transistors, those what they call pixels or picture elements. Okay, it's on the slide, but I didn't read that earlier. But you know, so a pixel is a picture element, which means it's one transistor. If it's a black and white, it's one transistor or diode in there measuring the light intensity. Or if it's a colored one, then it's got the red, green, and blue 3 transistors for every pixel. Okay. All right, so but what we're doing, again, back to the black and white here, is we're looking at as bright as it can be to as low as it can be. All right, so if it's as low as it can be, it's going to it's basically in that transistor. That transistor is going to be outputting a voltage of 0, which says it's dark, it's black. If it's about halfway intensity, then the voltage on that transistor is going to be about half the voltage it can be. Okay, and so half voltage means that it's going to be at 128, 127, 128, right around there. And then at full voltage, so when the transistor is outputting a full voltage, it's going to be outputting 255 is the value that the robot's going to see. So the transistors in the camera are actually outputting a voltage, and then that voltage is being sent to an analog to digital converter, and then it's generating a binary number. So for an 8-bit analog to digital converter, that binary number ranges between 0 to 255. So that's where that number comes from. So now when you have a part, so here's a couple of different parts in there. And what we're doing is we're showing how we can tell the location. Okay, so there's actually two parts of the CCD. The one part is where is it? Okay, so here's your, remember we had X going in the horizontal and Y going down. And so we're going over 1, 2, 3, and then we're going down 3. So this part starts at pixel number 3, 3. So this tells us, this gives us the X and Y, and then we can also, by looking at all of them, we could be able to tell the rotation of that part also. And then the other aspect of that is the intensity. So you can see here we got 255, 255, and then the grays are 128. So they're not black, but they're gray. So the values are 128 there. But so there's basically for the black and white camera, we have the we have 3 values that need to be stored for every transistor, or for every picture that we take. So each transistor has a location, okay, what row and what column the pixel is in, and then also what is its intensity. So all 3 of these values are needed to determine where the part is at, and so look at the intensity, but we need to know where it's at also in there. All right, so as I mentioned before, what the camera is really looking for is the edges of a part. Okay, what can it see? What can it not see? And so if we look at this grid here, when we have a part with a different shape, let me just, no, that's the part I want. All right, so so when we have the part that with a various shape here, right? So this part is black. So you look at the way down here, during the 4 bottom rows are all zeros. So this part is just reflecting absolutely nothing. So the camera is just seeing pure black here. All right, and then where the part isn't, it's reflecting everything, and so it's full intensity. But now here we have, right here in this middle row here, this part is halfway there. So some light is hitting. This is one transistor here. Let me get my arrow back here. All right, so this is one this whole square is one transistor. And so what we're saying is we're covering up we're covering up about half of the transistor. So it's getting about half as much light as the transistor above it. And so it's going to have that reading that's going to kind of be at the gray area of about 128. All right. And so we can see then that this is one straight line pretty much across here, because these four transistors are all getting just about the exact same intensity. All right. But then this here, right here, the part shoots up. And so it's covering up this area right in here. And so, you know, this one had 128 at half intensity, but this one here is getting more about 1/3 intensity. So it's dropped down to 70. And this one here just has a little bit of light right here and maybe just a little bit light right here. So it's dropped down even further to 50. And this one up here has most of the light, and it's just got this little bit of a triangle covering up just a small section of this transistor. All right, and so looking at all this, we can tell then the shape of this part, okay, and the orientation. But, you know, so we can, and what we're really looking for is this change between darkness, which doesn't have to be totally black, but in this example, you know, we're going from totally black to one pixel row that is half black, half light. So it's gray. It's right in the middle. We got this one here that's even less than that because it's mostly covered up. And then we've got this part which is even more covered up, right? And then like over here, we got this part which just has this bit on this left side covered up. So it's 191. All right. And so this is what the camera is really looking at. The camera really doesn't care about all this down here, and it really doesn't care about all this up here. What it cares about is the edges, where the numbers are changing. That's really where it's doing its identification at, okay, along those edges. All right, so you know, so the other thing then is colors, right? Even if they are a different color and you're using a black and white camera, you can still tell the contrast, okay? Sometimes it may not be hugely different, but you can see just a little bit of contrast right in here in between these. So these are slightly different colored objects, okay? All right, so this slide's just kind of trying to show the, you know, here is our top part. This is what we're looking for. And so when the next part comes down here and we're looking at it, we can see that it matches really well. We can see that this one, it looks the same, but it's much smaller. And so really to the camera, it looks completely different, right? Because it's not turning on the same pixels that the template part does. And then this here, we can tell this is the exact same part, but it's been rotated. All right, so that pretty much covers it for the vision systems. The other thing that I wanted to show you today, just very quickly here, we got a little bit of time, so is to talk about the barcodes. Okay. All right, so, and I know everybody's got to be familiar with barcodes. They've really been around for a long time, but they're